Welcome dear learners. We are continuing Unit 1, Chemistry as a Science Discipline and Scientific Analysis. The present module is entitled Representation of Analytical Data. The contents of this module we are going to discuss are units and measurement, significant figures in chemical measurements, rules for determining significant figures, accuracy and precision of chemical data. Finally, we are having some problems based on significant figures also. So, first of all, we are discussing units and measurement. You know about measurement in analytical chemistry. In analytical chemistry or in physics or in every branch of science, we are taking several measurements. For example, you can weigh a particular sample with the help of a balance. You can measure the volume of a liquid by using a measuring jar. You can measure the thickness of a material by using a screw gauge, etc. There are several kind of measurements we come across different disciplines of science. And here in this session, we are focusing on various measurements and their units. First of all, every measurement or measurement of any quantity involves comparison with a certain basic arbitrarily chosen internationally accepted reference standard. That is known as the unit. For example, the internationally accepted unit of mass is kilogram, that of time is second, that of distance is meter, so and so. So, there should be a unit for a physical quantity. Now, the result of a measurement of a physical quantity is expressed by a number accompanied by a unit. For example, I am measuring the length of a pen. Suppose it be 15 centimeter. So, 15 is the number, centimeter is the unit. In a similar way, there are unit as well as number for every measurement. The units for fundamental or base quantities are called fundamental or base units. However, in certain case, the units of other physical quantities can be expressed as combinations of base units. For instance, we are dealing with density. You know, density is mass by volume. Volume is expressed as meter cube. Mass is expressed as kilogram. So, the SI unit for density is kilogram per meter cube. So, unit of every physical quantities can be derived by using base units. This implies the fact that some measurements have base units, some other physical quantities have derived units. Such units obtained by derived quantities are called derived units. I mentioned about density. The unit of density is kilogram per meter cube. Kilogram per meter cube is a derived unit which is obtained from kilogram and meter. A complete set of these units, both the base units and the possible derived units, are known as system of units. Thus, in a system of units, there are some basic units and there are several derived units. Derived units are obtained by combination of base units. So, a system of units comprised of base units as well as derived units. Now, international system of units. You learned about System International or SI system. This is internationally reputed system of units, and there are some basic units for System International, and these basic units are total 7 in number. First one, Kelvin, which represents the temperature. Second one, meter, which represents the distance. Third one, ampere, which represents electrical current. Next one is second, which represents the time. Mole represents amount of substance. Kilogram represents mass. And finally, candela represents intensity of light. So, these are 7 basic units or 7 base units in the SI system of units. Now, what are metric prefixes? Suppose you measure the quantity of a substance or the mass of an atom. The SI unit of mass is kilogram. But for an atom, the mass is very, very small. So you have to use some prefixes to reduce the quantity, to represent the small mass. Therefore, you can use some prefixes. The prefixes are very much familiar to you. Prefixes can be used to represent small quantities as well as high quantities. The left hand side represents prefixes used to represent small quantities. They include deci, centi, milli, micro, nano, pico, femto, atto. And the quantities, the prefixes used to represent high quantities include deca, hecto, kilo, mega, giga, tera, peta, exa. See, exa stands for 10 raised to 18, which is used to represent bigger quantities. Nano stands for 10 raised to minus 9. You are familiar with the nanomaterials, etc. 10 raised to minus 9. Minus 9 is the prefix nano, indicated by the prefix nano. So, atto stands for very small quantity, that represents 10 raised to minus 18. So, by using these metric prefixes, you can represent small quantities as well as bigger quantities. Moving on to another important area of this discussion, that is significant figures. Significant figures are very important as far as a particular measurement is concerned. Significant figures, otherwise called significant digits, are the digits in a number that carry meaningful information about its precision. Meaningful information about its precision. For instance, I am representing some quantities to you. I measure the weight of a particular substance. Let its weight is 20.1 gram. 20.1 gram. In some other measurement, I got it as 20.10 gram. In some other measurement, I got it as 20.102 gram. In some other measurement, if I got the mass as 20.1024 gram. See, among these 4 measurements, my simple question is, which measurement is more precise? Which measurement is highly informative about the mass of the body? This is 20.1. So, the last digit 1 may have some uncertainty. It may be 0.09 or 1.1 like that. There is always some uncertainty associated with the last digit of a measurement. Now, it is more clear. It is 20.10. This is 20.102. The last measurement, 20.1024, is more precise. So, in the last measurement, there are 6 significant figures or significant digits. However, in the first case, there is only 3 significant digits. So, with the increased number of significant figures, you will get more meaningful information about its precision, about the precise value. Now, we are considering significant figures definition. Significant figures are the number of digits in a value, often a measurement that contribute to the degrees of precision of the value. That is, higher the number of significant figures, more precise will be the measurement. Higher the number of significant figures, more precise will be the measurement. Now, significant figures in a measurement is theoretically sum of two things: the reliable digits and the first uncertain digit. This point I can exemplify with the help of a measurement. For example, if we say the mass of a substance is 1.62 gram, the first two digits, that is 1 and 6, are reliable digit and certain digits. There is no uncertainty with the first two digits. However, the last number of a measurement is always uncertain. So, in 1.62, the last number 2 is known as uncertain digit or insignificant digit. So, the sum of reliable digit, that is 1 and 6, and the first uncertain digit or insignificant digit is known as the total number of significant figures. So, here in this measurement 1.62, the total number of significant figures is equal to 3. 1 and 6 are certain and reliable figures or digits, and the last number 2 is uncertain. So, you have to take first uncertain number and 2 reliable number. The total number of significant figures here is equal to 3. We can take several detailed examples in coming slides, and we have to discuss more things about the significant figures. Thus, the measured value, this 1.62, has a total of 3 significant figures. Now we are focusing the rules for determining significant figures in a measurement. This is one of the most important aspects of the analytical chemistry, analytical science. In every analysis, you have to make several measurements. In order to increase the precise nature of the measurement, you have to think about the number of significant figures. Higher the number, higher will be the precision. So, to find out the number of significant figures is made by adopting certain rules, and we are focusing on that rules to determine number of significant figures. The rules are here. The first rule is like this: all non-zero integers are significant. That is, in a measurement, all non-zero digits that appear in a measurement are treated as significant figures. This point we can illustrate with some examples. Let the measurement is 412945. Here all are non-zero digits. All non-zero digits are significant. So, in this quantity, there are 6 significant figures. Take another one, that is 12.45, which has all quantities are non-zero. So, here there are 4 significant digits. So, the first rule is like this: all non-zero integers are significant. We are now discussing the second rule. This is most important. This is about exact numbers. All exact numbers have unlimited number of significant figures. Then what do you mean by the term exact number? Then how you will get exact number as a result of a measurement? The examples will tell you more details. See, if you count the number of pupils, number of students in your class, then you start counting from one end to other end. Then you got the number as 35. That means 35 pupils are present in the classroom. So 35 is a fixed number. That fixed number have unlimited or infinite number of significant figures. Another example is, it has been determined the fact that there are 60 seconds in 1 minute. So, the 60 is a very certain quantity, is a fixed number. That fixed number 60 here has infinite number of significant figures or enormous or unlimited number of significant figures. Now, the third rule, and there have so many subsets for the third rule, and the third rule is about the significant nature of zeros. Zeros are significant depending on what kind of zeros you are having. So, look at the first sub-rule. Zeros that are between non-zero integers are always significant. Remember, zeros that are between non-zero integers are always significant. So, you can check whether a given zero, whether 0 present in a given measurement is significant or not. That depends on several rules, depends on several conditions. Depending on what kind of zeros they are, that is an important point. So, 0 may be significant or may not be significant, depend on the condition. What zeros you are dealing with. For that, we are using some subdivisions or sub-rules. The sub-rule A deals that zeros that are between non-zero integers are always significant. This can be illustrated by this example. The zeros in 1000045, 6004545 and 23.04 are all significant because they are between non-zero integers. Look at the first quantity. Here 3 zeros are there, but all zeros are present. Between non-zero numbers. Here these 2 zeros are present between 6 and 4. They are non-zero numbers. In the case of 23.04, that 0 is present between 3 and 4. So, you can say that that 0 is also significant. So, look at these rules. Zeros that are between two non-zero digits are always significant. Now, moving on to the second subset, second sub-rule. Zeros that come before non-zero integers are never significant. Zeros come before non-zero integers are never significant. Look at this example. The zeros present in 098. Here the 0 is present before non-zero integer. This is 9 is the non-zero integer. So, this 0 is present before 9. That is not significant. Here this is not significant. All these zeros are not significant because they all present between a non-zero digit. Now, look at the third sub-rule. If the zeros come after non-zero integers and are followed by a decimal point, that is a decimal point, the zeros are significant. This point is significant if zeros come after non-zero integers followed by a decimal point. Then zeros can be considered as significant. This example will tell you the things. The zeros in 1000 points, 1000 with a point, there is a decimal point. So, all these zeros are significant because the number ends with a decimal point. Now, there is subset, there is sub-rule. If the zeros come after non-zero integers, but there is not followed by a decimal point. In the previous example, there is 1000 followed by a point. But if there is no point, the zeros are not significant. Look at this measurement. The zeros in 1000, here you cannot see a decimal point. Here there are 3 zeros, but zeros are not end with a decimal point, such that these zeros cannot be treated as significant figures. Now, the last sub-rule associated with zeros is this one. If zeros come after non-zero integers and come after the decimal point, they are significant. Some zeros may come after the decimal point, but if it come after non-zero digit and come after the decimal point, you can count it as the significant figure. This example will illustrate the things. Here you look at this measurement, 9.89000. Here the 3 zeros are significant. Why they are significant? The zeros are coming after the decimal point. Moreover, they are coming after a non-zero digit. That's why all these zeros are significant. There are several rules we have discussed in order to find out the number of significant figures. And these significant figures, we have to adopt, we have to utilize the significant figures rules in addition, subtraction, multiplication, division. They are different mathematical procedures. We have to look on what are the rules associated with the mathematical procedures. Now, rules for arithmetic operations. We are discussing addition and subtraction first. We are focusing on addition and subtraction first. When adding or subtracting, the answer should have same number of decimal places as in the limiting term. As in the limiting term. Decimal places means the number of places coming after the decimal point. So, what is a limiting term? The limiting term in the number, the limiting term is the number with least decimal places. With the least decimal places. Suppose there are three quantities like 20.1, 20.12, 20.123. These are three numbers. Can you try to find out which one is the limiting term? The limiting term is one with the least number of decimal places. This is applicable to the arithmetic operation addition or subtraction. Same rules for addition as well as subtraction. So, three quantities are in front of you. Here there is only one decimal place, two decimal place, three decimal place. So, the number with the minimum number of decimal places are said to be the limiting term whenever you are dealing with the addition and subtraction. Now, we can illustrate addition and subtraction by taking some examples. You look at these quantities. Here I am adding four different quantities: 6.22, 53.6, 14.311, 45.09091. Now, let us find out the number of decimal points in each and every quantities. Here there are two decimal points, only one decimal point, three decimal point, and five decimal points are here. So, in this measurement, the quantity with the minimum decimal point is 53.6. That is the limiting term which is having only one decimal place. So, whenever you are performing the addition, your final result also contain only one decimal place. This is the actual result of addition, but in order to represent it based on rules of significant figures, you have to represent only one decimal place. So, 0.22191 should be rounded off to 0.2. Others should be ignored based on rules of rounding off. So, whenever you are adding or subtracting some quantities, the final result must have decimal places similar to the limiting term. This can also be illustrated with the help of subtraction. We are subtracting two quantities. Here there are three decimal points. Here there are five decimal points. Absolutely no doubt. The limiting term has three decimal points. So, the first one is the limiting term. So, whenever you are performing the subtraction, you will get the actual result like this, but the final result must have three decimal places. So, this 33194 should be rounded off to 332. This is the rule of significant figures associated with arithmetic operation addition and subtraction. Now, we are discussing arithmetic operation multiplication and division. In the case of multiplication and division, the rule is somewhat different from addition and subtraction. Look on this rule. When multiplying or dividing, the answer should have same number of significant figures as the limiting term. Then, what do you mean by the limiting term here? In multiplication and division, the limiting term is the term with the least number of significant figures. This is most important. When we discussed the case of addition and subtraction, the limiting term is the term with the minimum number of decimal points. But in multiplication and division, the limiting term is the term with the least number of significant figures. So, in multiplication and division, you have to check on significant figures number And in addition and subtraction, you have to check number of decimal points. This is very, very important as far as arithmetical operations are concerned. Now we can exemplify multiplication and division. Consider the first example. 503.29 multiplied with 6.177. These are two quantities. And on multiplying this, I got this result in the scientific calculator. But look on this quantity. In this quantity, there are 5 significant figures. In the second quantity, there are 4 significant figures. And I mentioned in the rule that those number with the minimum number of significant figures is termed as the limiting term in the course of multiplication and division. So here there are 4 significant figures. So you can treat it as the limiting term. So limiting term contains 4 significant figures. Therefore, the final answer must also contain 4 significant figures. So this has to be rounded off to, this term has to be rounded off to 4 significant figures. So I have to exclude all these numbers because I have to use only 4 significant figures. So this term is rounded off to 3109. We will discuss the rules for rounding up in coming slides. Okay. Now we can take another operation, that is division. Look at this example. 1000.1 is dividing with the 243. The result, the actual result is 4.11563,786. But look at the number of significant figures here. Here there are 3 significant figures. Here there are 5 significant figures. But you should keep the fact that the result contains 3 significant figures only. So this quantity should be rounded off to 4.12. That means there are 3 significant figures. So in the case of multiplication and division, the result contains same number of significant figures as that in the case of the limiting term. Limiting term is a term with the minimum number of significant figures. Now we are discussing conversions, unit conversions, etc. For instance, you can express length of a body in millimeter, meter, kilometer. There are several units. But interconversion of this unit will not alter the total number of significant figures in a measurement. This is very, very important. That is a choice of change of different units. You convert a millimeter to centimeter, centimeter to meter, etc. Several conversions are possible. But that conversions will not alter the total number of significant figures in a measurement. This I can illustrate with the help of a particular example. For example, the length of a particular body is measured originally as 2.308 centimeter. Here you can see the presence of 4 significant figures. 4 significant figures. You can express it in some other units like meter, centimeter, millimeter, etc. When it is converted to meter, you have to divide it with 100. So it is converted to 0.02308 meter. You can convert it into millimeter. Then the result is 23.08 millimeter. You can convert it into micrometer. Micro is 10 raised to minus 6. So you can perform this operation, micrometer. As a result, you will get to 23080 micrometer. You check on all these quantities. Here there are 4 significant figures. Here also 4. In the last measurement also 4. Therefore, it is very well clear that interconversion of the units will not alter total number of significant figures which are originally present. This is a most important rule associated with the conversion or interchange of different kind of units. Now, there are some other examples for the conversion also. You are very familiar with the feet and inch. You know 12 inch equal to 1 feet, which is a very popular common measurement. 52.4 inches are there. I wish to convert it into feet. So, 52.4 inches divided by 12 inches. In order to convert inches into feet, I have to divide it with 12 because 12 inch is equal to 1 feet. So, 52.4 inches are there in total. Here you can see the presence of 3 significant figures. I have to divide it with 12. I have to divide it with 12. Here there are 2 significant figures and 1 decimal point. So as a result, the final result should be round off to be 4.37. Here there are 3 significant figures. As when inch is converted to feet, inch is converted to feet, that feet also contain 3 significant figures. Here you can see the presence of 3 significant figures. That is the final quantity. This simply you have to keep like this. You can use any unit to measure, to express a particular quantity. Changing the units will not alter total number of significant figures. Now, another part of the discussion is about rounding of the quantities. This is very popular whenever you are dealing with the mathematical problems or solving some problems with the help of scientific calculators, etc. The rule by convention is that the preceding digit is raised by 1 if the insignificant digit, what is insignificant digit? The digit to be avoided, that is called insignificant digit or uncertain digit. The uncertain digit to be dropped, to be removed is more than 5 and is left unchanged if the latter is less than 5. This we can illustrate with the help of some examples. You look at this quantity. This is 2.746. Here there are 4 significant figures. I wish to drop 1 significant figure. This 4 to be reduced to 3 significant figure. How I can perform that? So, this means you have to avoid this 6. 6 is greater than 5. So, you have to remove 6 by adding 1 to the preceding number. What is the preceding number here? 4 is the preceding number. This is removing number. This is the preceding number. Since the removing number or insignificant number is greater than 5, you have to add 1 to the previous number. So, this 2.746 is now changed to 2.75. 4 is the preceding number which is raised by 1 unit. Now take another example, 1.743. You wish to remove the last number 3. Here 3 is less than 5. So you simply drop that 3 because it is less than 5. So simply drop. You need not change the preceding number. So the result should be equal to 1.74. This is the general rule for rounding off. Now a question may appear in front of you. If the insignificant number is 5, not greater than 5 or less than 5, if it is sharp of 5, what will be the procedure? Your answer is here. In the case the insignificant number is 5, you have to follow this rule. What is that rule? If the preceding digit is even, the insignificant number is simply dropped. The 5 can be dropped. And if the preceding number is odd, you have to increase the preceding number by 1. This we can illustrate with the help of this example. Suppose you wish to round off the number 2.745. 2.745 to be rounded off. Fortunately or unfortunately, the last number is sharp 5. It is not greater than 5 or less than 5. So the number is 5. So 5 can be dropped if the preceding number is even. The preceding number is even. So the preceding number 4 is an even number. So you can simply drop 5 and the result is 2.74. Now look at this example. The number 2.735. You have to remove this number which is exactly 5, but the preceding number is an odd number. So whenever you drop 5, you have to add 1 to the preceding number. So the preceding number is now changed to 2.74. These are all about the rules for rounding of a quantity, rules for reducing the number of significant figures in a measurement. Now, we have to discuss scientific notation. In scientific notation, every number is expressed like this: a into 10 raised to b. Any quantity can be represented like a into 10 raised to b. Remember, the first number a is between 1 to 10 and b is simply any positive or negative quantity or the power of, represented as the power of 10. You can call it as exponent. See, for example, 5 into 5.2 into 10 raised to minus 8. This is a scientific notation. This can be represented as a scientific notation. But this cannot be written as 52 into 10 raised to minus 9. This is not a scientific notation. The first number should be between 1 to 10. The 10 raised to power may be positive quantity or negative quantity. Let us look at some examples. Here there are the diameter of earth diameter. Earth is a very big body. Its diameter is very big number. It can be expressed as 1.28 into 10 raised to 7 meter. Now, Avogadro number, which is very popular number to every chemist, every chemistry student, every chemistry teacher. Avogadro number is the number of particles present in 1 mole of a substance. You are familiar with that. It is abbreviated as N0. Okay. It can be represented in scientific notation like this: 6.022 into 10 to the power 23. Here, the 10 to the power is a positive quantity, 10 to the power 23. So, these are about the scientific notation. Now we are considering another area, that is accuracy and precision. In scientific measurements, accuracy and precision are two distinct concepts used to describe the quality of data. Accuracy refers to the closeness of a measured value to a standard or known value. Some examples are there. If the actual boiling point of water is 100 degrees Celsius and a measurement gives a value of 99.9 degrees Celsius, you can say that these two values are very close. Hence, you can call it as an accurate measurement since it is very close to the true value. Now, some examples are here. If in a lab you obtain weight of a measurement 3.2 kilogram for a given substance, but the actual weight is 10 kilogram. So, instead of 10 kilogram, you go to 3.2 kilogram. See the difference between these two quantities. So, you can say that the measurement is not accurate. In this case, your measurement is not close to the true value. If there is very closeness, the result will be accurate. Now, accuracy tells you how correct your measurement is compared with a standard or a known value. Another term is precision. In coming modules, we can discuss more about the precision. Here I am saying only for the sake of the definition and simple understanding. Precision refers how consistent repeated measurements with each other regardless how close they are to a true value. See, for example, if a balance consistently measures the mass of an object 5 gram, 5.00 gram, 5.01 gram, 5.00 gram, you go to 3 measurements. See the range of the measurements, they are very close to each other. There is only small difference. So, these 3 measures are said to be precise measurements. Now, precision is independent of accuracy. If you go to some precise values in repeated measurements, that doesn't mean accuracy. Precise values may or may not be accurate. Precision indicate reproducibility or reliability of the measurement. This is a comparison between accuracy and precision. See, here this is arranged, this is a play, and here we are in the first play. The target is at the center portion. Every hit is on the target itself. There is no difference. So, this is good accuracy, good precision. But in the case, the original target is at the center, but the hit is on outside. So, poor accuracy, but good precision. All are hit on the same point. But you look about the last measurement, nothing touches at the center. So, there is poor accuracy. And all are at different areas from the center point. So, poor precision. So, precision doesn't mean accuracy. Now, we are discussing some problems associated with this concept. The first one, how many significant figures does each of the following contain? These are some quantities. We can look onto the answer to this based on the rules we have studied or understand. This is 54. This is a quantity. Definitely all non-zero digits are significant. The number of significant figures equal to 2. Here there is a 0. 0 lies between two non-zero digits. So total 3. All 3 are significant. Here 4.00. 4 is significant. 2 zeros are also significant because the zeros are coming after a non-zero digit after the decimal point. Here there are also 3. But here there is in 400, there is no decimal point at the end. So these 2 zeros cannot be considered as significant. So here there is only one significant figure. In the case of 0.041, this represents, this 0 is coming after a 0. So this 0 cannot be treated as significant. So here there are 2 significant figures. And in the next problem, here this 0 can be avoided. All other zeros can be counted. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 significant figures in this measurement. And in the last case, the first 3 zeros cannot be treated as significant figures, but 1 is significant. The last 0 is significant because it is coming after non-zero, after decimal point. So in the last case, there are 2 significant figures. Each side of a cube is measured to be 7.203 meter. What is the volume of the cube to appropriate significant figures? You know, length into breadth into height. Since it is a cube, A equal to B equal to C, all edge lengths are same. So you have to take the cube of 7.203. Here there are 4 significant figures. On taking the cube root, on taking the cube of this quantity, the final answer must also have 4 significant figures, because this is the one and only term, that also is the limiting term. So the answer appears like this. The calculated volume should be rounded off to 4 significant figures. The reason is simple. In this term, there are 4 significant figures. Therefore, volume of the cube is A cube, or 7.203 the whole cube. Meter cube is the unit. On taking the cube of 7.203, the value you got is this, but you have it to round off to 4 significant figures, since the quantity, the limiting term, the one and only term contains 4 significant figures. So this big quantity should be reduced to 4 significant figures, that is 373.7 meter cube is the final answer. Thus, in this session, we have studied many aspects associated with the significant figures and practiced several problems. That all about the present module. Have a nice learning experience. Thank you.